Okay, we're going to continue our discussion of how we can work with equilibrium constants. And one thing that we need to note is that it's often necessary that we proceed with a reaction in a way other than exactly how it's written. And so in order for us to do that, we have to know that we can treat them somewhat like Hess's law, and we can then apply certain conventions to the equilibrium constants to reflect the changes that we make as we're changing the way they're written. So the first of these involves reversing a reaction. If I have A going to B in equilibrium and I want to say B going to A in equilibrium, all we need to do is reciprocate or flip that value. So we saw earlier that K forward over K reverse equal to constant. Because they're related by that constant, if I want one or the other, I just solve for it, and it ends up reciprocating it with a constant. We ignore the constant, so we just look at the reciprocal. If we change the stoichiometric coefficients, like in a Hess's law problem where we might multiply everything by 2 or multiply by 3 or whatever, when we do that, we raise the value of K to that power. So, for example, if I take the reaction A plus B goes to C and double everything, I'm going to square the original K. So the K for the original reaction squared equals the K for the new reaction. That should make sense because if I put a 2 in front of everything, essentially I've changed all these from coefficient or exponents of 1 and coefficients of 1 to exponents of 2. And so that will, in effect, square the entire expression. Then the last thing we see is if I add equations, I just multiply their K's. So, for example, if I have A goes to B and C goes to D, and I want to add those reactions together, this is K1, this is K2, then down here, down here I get A plus C goes to B plus D. My new K for this expression is going to be K1 times K2. That's all we're saying. All right, when we're dealing with heterogeneous equilibria, essentially what we're saying is that we have everything in, homogeneous equilibria, we're saying everything's in the same phase. So by that notion, heterogeneous equilibrium should be whenever I have things in multiple phases. So maybe I have a solid and a liquid in contact, or a liquid and a gas in contact, something along those lines. But what we do is we omit solids and pure liquids from equilibrium expressions because their concentration in themselves is a pure value. For example, the molarity of water in water is always 55.5 moles per liter. You can prove this to yourself if you'd like, or you can trust me that it's true. And since they're constants, we just omit them and build them into the equilibrium constant as a collection of constants. So, for example, when I have PbCl2 solid going to Pb2 plus aqueous, 2Cl minus aqueous, essentially because this is a pure solid, it's going to be constant. So Kc for this reaction would be products over reactants, concentration of Pb2 plus times concentration of Cl minus aqueous squared. Sorry, your 2 plus should be inside here. My bad. And that would be divided by PbCl2. But the concentration of PbCl2 in PbCl2 is a constant. So I'm going to say constant. And so really this is equal to K times, which is equal to, Pb plus 2 times Cl minus squared. And when we do this in a situation like this where I have a solid dissolving, we would actually call this KSP, K solubility product, where these two things are going into solution activity. So always omit pure solids and pure liquids. Now, in heterogeneous equilibria, we can also do the following. I can exclude the solvents from that expression as long as the concentrations of anything dissolved in them is really, really low. If it's really, really low, we can approximate that they're pure, and the activity changes for the solvent will be very small, so we can omit them from the equilibrium constant. For example, if I'm looking at water reacting with carbonate to make hydroxide and hydrogen carbonate, I will find my H2O. Yes, I know it's got stuff in it, but we're going to assume it approximately pure as long as the concentration of CO3 2- is small. If that's the case, then my concentration-based equilibrium constant, Kc, will be products hydroxide times hydrogen carbonate divided by reactants that are not pure, CO3 2-. So essentially we're going to remove the water. All right, sometimes it's going to be necessary for us to do more with these constants than just write them. In that case, we're going to employ something called an I diagram. And so a lot of times we won't have all the information we need to calculate K, but I'll have other pieces of information, and I'll have the stoichiometry of the equation that will allow me to get to that information. And so we also need to remember that pressure and molarity are proportional, so we can use this for gases as well. When we do this, it's called an ICE diagram, where the ICE stands for initial, change, and equilibrium. So this is going to refer to the concentrations or pressures of the species at those 3 points. So an example of this, if I take a closed system that has 1.0 times 10 to the -3 molar H2 and 2 times 10 to the -3 molar I2 at 448 and allow it to reach equilibrium, and then measure it, I see by analysis that the equilibrium has a concentration of HI that is 1.87 times 10 to the -3 molar. They want to know what Kc for this process is at 448 degrees Celsius. So something of importance to note, temperature does not change, so I don't have to worry about any change in K due to that. They don't tell me the volume of the system, so I'm going to go ahead and assume 1 liter vessel because it won't matter. That'll just make my calculations easy. And then I'm going to take the equation and rewrite it so that I have more room. I'm going to have H2 plus I2 becoming 2HI. And then I'm going to make my ICE diagram. So we're going to have initial concentrations, changing concentration, equilibrium concentrations. So initially, according to this, if I have 1.00 times 10 to the -3 molar H2 and I have 1 liter of H2, that must mean I have 1.000 times 10 to the -3 moles. Reactions happen mole to mole. Initially, for I2, I have 2.000 times 10 to the -3 moles. And for HI, initially, there is none of this. It has not had a chance to react yet. We charged it with reactants. And then at equilibrium, it tells me HI is 1.87 times 10 to the -3 moles per liter, which for in 1 liter means moles. So the change in HI then had to be positive 1.87 times 10 to the -3 moles. And so we gained that much, so I went from 0 to 1.87 times 10 to the -3. Now I need to use stoichiometry to relate what happens to these guys to what happens to HI so that I can see what my equilibrium concentrations are. I know that H2 should go down because it's on the opposite side by the same amount of HI. So for every 1 H2 that I have, it's going to take one of those to make 2 HI. So I'm going to have twice as much H2 going, half as much H2 going every time I make an HI. So I had 1.87 times 10 to the -3 molar, or moles. Same thing is going to happen for my I2. I'm going to lose 1/2 of 1.87 times 10 to the -3 moles. And if that's the case, then all I have to do is subtract my values. So if I take 1 minus 1/2 of 1.87 times 10 to the -3, that is 6.5 times 10 to the -5 moles. And if I take 2 minus that amount, I get 1.065 times 10 to the -3 moles. And so these are the values that I have for my equilibrium concentrations. So then if I want to know Kc will just be those concentrations. I'll have 1.87 times 10 to the minus 3 squared divided by 6.5 times 10 to the minus 5 to the first power times 1.065 times 10 to the minus 3, all to the first power. And I can find that value. You can do that later and prove to yourself that it works. All right, another example for the Haber process. I've got nitrogen reacting with ammonia to produce, or reacting with hydrogen to produce 2 molecules of ammonia, and they give me the Kp value. So I'm going to go ahead and rewrite the equation here so we can work with it. I'll have N2 plus 3H2 will make 2 NH3. We know this is going to be an ice process, so ice. And they're telling me the partial pressure in the equilibrium mixture, so they're going to tell me the equilibrium mixtures. So the partial pressure of H2 is 0.928 atmosphere. The partial pressure of N2 is 0.432 atmosphere. And they want to know the partial pressure of NH3. So this is a question. And I also know that the equilibrium constant for this expression, Kp, equals 1.45 times 10 to the minus 5 at 500 degrees Celsius. And so all I have to do now is work this down. Now, what I don't have to do is I don't have to fill this in. This is really not a nice problem. My bad. But we do have an equilibrium expression and values that I can put into it. So I should know that Kp is going to equal the concentration of NH3, or pressure of NH3, squared, divided by the pressure of N2 times the pressure of H2 cubed. Now, I actually have values for this. So I'm going to say 1.45 times 10 to the minus 5 should equal the pressure of ammonia, which is what I want, P NH3 squared, divided by the pressure of nitrogen, which they told me is 0.92. Oops, I did these backwards. This should be 0.928, and this should be 0.432. So N2 is 0.432 to the first power, and H2 is 0.928 to the third power. And so I can solve that and see what the pressure of NH3 is. And you can do that on your own. All right, again, I'm going to stop here so that we don't run out of time, and we'll complete this lecture in another, or complete this series in another.